Thank you, Sam, for introducing me. But the thing is, I'm not really sure whether I'm that knowledgeable or my pictures are that worthy. But anyway, I know a few things so that I can tell you. Um, anyway, thank you very much for the invitation. So my interest in stars goes a long way. This is the uh, basically a definition that I found in Google. It is photographing the astronomical objects and basic celestial events and areas of the night sky. That's pretty broad, I understand, and it's also called astronomical imaging. So my interest goes on pretty long in my life. So my grandfather used to carry me and show me all stars, and then he called some of them stars, some of them worlds, and then I can still remember I could get the Orion's belt every time. So that's how I started. This is a hell of a long time ago. So this is Orion, and that is the Orion's belt. And if you see this little blob, that is the Orion Nebula, which is at the tip of the sword of the Orion. So anyway, you'll see that this big yellow star, which is called Betelgeuse, for all your knowledge. So it's called Betelgeuse, which is a bit hilarious, but then anyway, that's a star which is, I think, is going to go into a supernova within about next 200,000 years. So we would be seeing it anyway. So that's one of them. So this is Orion's belt in close proximity. I mean, none of these pictures are mine. Just this is, I wanted to show you what Orion's belt looked like in close proximity. Anyway, so then while long after that, I was having I had a late night and was getting into the car and looked at the night sky. There was no stars, absolutely none. So basically, then I did not realize that the light pollution has come to Colombo. But anyway, now I know it was light pollution, big time. So to continue the story, there are two main broad groups of imaging. One is wide field, and other one is narrow band. So it is basically, there is always intermixing of these two fields. So the person who takes a wide field picture would take one or two narrow bands, and the person who only does narrow band would take a sort of wide field picture too, because usually it is breathtaking when you look, when you see the Milky Way in its full glory in night sky. So I had my interest for a long time. However, I got into a group of people who did this in very meaningful way. So I went with them to a dark sky site. So there are about one or two in Australia, and it is all over the place. There are these dark sky sites where they even keep the street lamps covered, and they are with a less sort of illumination. They cover it. They cut them off at about 10 o'clock in the night, and that is in the town part of it. But this place is where Anglo-Australian telescope is. So this is about 1,000 meters high, and there's absolutely no light close by. So it is it's slap bang in the middle of a national park. So basically, that's a brilliant place. So this Anglo-Australian telescope is it's in a group of telescopes where they do lots of science. So that was a good place to be in. So my wide field also was in that site, and I had one or two sort of forays into narrow band, which is pretty complex. But the thing is, it's very enjoyable when it goes right. but most of the time it goes wrong, for me that is. So usually my guru who taught me all this is a guy by the name of Christian Sasser, who is a German chap who specializes in optics. And he's known to photograph the most distant object or celestial object in the world. So anyway, the good thing is that he has a connection to Sri Lanka. His father was sort of ambassador to Sri Lanka from West Germany. So this guy has roamed around Sri Lanka left, right, and center. He knows places that I have never heard of. So so we had a long chat about Sri Lanka and what it is now and all those things. Anyway, he told me his first thing was that you should be using your own equipment. You should never buy anything just to do this. So anyway, I took that advice, but the thing is, without telling him, I went and bought few things. I mean, as usually we do. So I went and bought one of those ball heads, which has a coarse adjustment as well as a fine adjustment. It's a fine adjustment, and also a tripod, which which I thought should. I mean, I think it went the wrong way because this tripod is a very light tripod. It's practically carbon fiber tripod, which is very light. But then there has to be a very sturdy tripod to do all these things. And wide-angle lens that I bought initially as Samyang 14 millimeter prime lens, which was about 600, no, not 600, about $300. I mean, Australian dollars that I'm talking about, and that has got real bad sort of vignetting and all those things. But anyway, just went on with it. Went to this place and started photographing. And then I'll just digress a little bit to say what narrowband is. So narrowband is basically one would image very narrow bands from that color visual field. So one is hydrogen alpha, which is a one thin line, and oxygen 3 and sulfur 2. So this has got separate sort of filters, which only transmit these. So basically, you can image these very narrow areas of this electromagnetic field of visible light. So that is what this narrowband photography is, or astrophotography is, that is. So to go back to my equipment, I'm sorry that I haven't got pictures of what I use, but that's nothing special that I use in the first place. So it is a DSLR. Usually I used till about 2016 to about 2019. I used my Canon 5D Mark III. Nothing special, but in 2020 I bit the bullet and bought a Canon EOS RA, which is an astrophotography, specialized astrophotography camera from Canon. But anyway, from that time onwards, I'm stuck at home. So can't go anywhere. So because of the pandemic, that is. And it has to have, it could be a mirrorless, as RA is practically a mirrorless camera. And you can have a wide angle lens and very sturdy tripod. And most importantly, the most important factor, dark skies. So if you have a dark sky, then all glory is in front of you. So that's brilliant to see. So dark skies are a thing that is vanishing fast from the world, except in sort of designated dark sites. Most other places have no regard for light pollution, I think, even though there is a society trying to attract people to talk about light pollution. So there's this guy called John Bortle who classified nights. He died in 2011 or 12 at the age of 102. So anyway, this chap went from bottle class 1 to 9. So 9 was in a city, which, as you see from the picture, there's absolutely nothing that you can see in the sky. And then suburban skies, which you can see one or two really bright, I think, planets, most probably, not even stars. And then bottle class 5, you'll see the brightest possible stars. Rural sky is the bottle class 3, you'll see lots of stars. But the thing is, the excellent dark sky would be a bottle class 1, which is like which is at the site of the Anglo-Australian telescope. So anyway, that's the classification of it, and this is the picture of the man. I haven't met him, but there are lots of people who have met him. The good guy, it seems. So you can actually find where the dark skies are. So there's this site, it's a website which will give you absolute brilliant, almost up-to-date information about dark skies. And that's one of the best resources, and it is free. It has got Sri Lanka too. That's Sri Lanka having dark skies. So all the national parks, if you see, that is Vilpattu and Yala and Galloya, all these places are practically dark skies. They have no light. I think that little blob in this Yala is, I think, was probably Kataragama, because Kataragama is right in the middle of Yala. So anyway, that is Sri Lanka. That is where I live, Melbourne. So you see that I have got huge amount of dark skies. So this is only state of Victoria. So that goes from that bit is state of Victoria. I have a huge amount of dark skies. Only thing that I don't have is time to travel. And these 2 years, there's no way of traveling either. So I actually spoke to a chap today who is the chief of astrophotography in. It is actually he's the chief of astrophotography of the Astronomical Society of Victoria. So basically, I'm going to hook up with him to see whether I can do remote imaging in his dark side. So let's see how it goes though. So as I said, it is 5D Mark III, made out just bought it in 2012. This is a comparatively old camera. So it is only for wide field imaging. Basically, image sensor seems to be very important. Everybody I talk to, they say that you need to have a full frame sensor, but I have seen many pictures that have been taken with crop sensors are far better than mine, I can tell you. So there's I don't think it is the sensor that is important. It is what's behind the camera which is important. And also pixel size. They make a huge amount of issues about pixel size, but the thing is, I think that is also completely nonsensical. I don't think pixels at my level, at least, pixel size does not matter in that sort of sense. And also, the other biggest thing is that you need to be able to focus. As Roshan said 2 days ago, you just cannot focus in the night by having autofocus. That doesn't work. And Roshan was talking about cityscapes, but I'm talking about dark skies. So it does not work. So basically, that's one of the main issues. And also shutter speed, which has to be slow. I usually with the 5D Mark III, I go at about 20 seconds at 14 millimeter lens, 20 seconds. So basically, that's one of those things that need to be looked at. And I go at just go at ISOs of about 6,400. So I don't think that makes matters too grainy. But anyway, you can decide when I show sort of one or two of my pictures. The biggest thing is not to touch the camera, as Roshan again alluded to in 2 days ago. So basically, I have a remote trigger, remote triggering cable, and also I have bought a Wi-Fi, so electronic shutter cable, plus sort of, I think these newer cameras has got their sort of photo sort of this time lapse. You can make it from inside the camera, so you don't need to touch it anyway. And the other biggest issue here is that this is really dark, so it takes about 30 minutes to get your eyes sort of accustomed to the dark, and then with the whole Milky Way up there, you can actually see your own shadow because it is so bright. You have to remember it is thermonuclear sort of fusion up there going on in every little dot of that. So the moment you kick the tripod leg, then that frame has to go. That's about it. That's gone. So, but the good thing is that this is a digital camera. You can delete whatever you want, the way you want. So that's not a problem in that sort of sense. So this is the picture that I put in for that flyer, taken from my trusty 5D Mark III, Semia 14mm 1.8. This I had it at 1.8. This is from not my memory, it is from EXIF data. And it was ISO 6400 and auto white balance. However, I see this yellowish cast at lower edges of the film of the frame. I'm not really sure where that is from. This so that is the Anglo-Australian telescope that I was talking about. They are so imaging something. You can see the track door open, and this red light. It is not a red light. It is there's a microwave link which we get internet there from ANU. That is it is actually from which called Australian National University. There's a microwave link to that. So I had never seen microwave links sort of light up in the night because there's 20 seconds of it. So obviously there's a little bit of light being emitted there. So, and the other thing that I want to show you is this little smudge in the middle of all. So this is the Milky Way, part of it at least. The little smudge that is below. So that is called large Magellanic cloud. It's not seen in northern hemisphere. It is only in southern hemisphere. All the astronomers that I have met told me that southern hemisphere skies are far more interesting than the northern. However, to show you another side of the story, Sri Lanka, I mean, southern tip of Sri Lanka is about 600 kilometers from the equator. So Sri Lanka is in the northern hemisphere, first thing. So basically, there are two northern and southern celestial poles. So those are extensions of North Pole and South Pole to space. So the world rotates in its axis. North Pole and South Pole are basically static. And if you think about North Celestial Pole and South Celestial Pole, they'll be static too. So basically what I'm trying to say is that if you aim your camera towards North Celestial Pole, you will get and if you have a long exposure, I'm not talking about 20 seconds, I'm talking about multiples of 20 seconds and putting them together, there'll be star trails, with concentric star trails, with the center being the celestial pole. So anyway, so that is in Sri Lanka. If you're talking about Sri Lanka, the North Celestial Pole will be closer to the horizon because Sri Lanka is just almost at the equator. Where I live, it is about 40 degrees from the horizon. So basically, south and the good thing is North Celestial Pole has got this polar star, which is almost at the pole. But then if you go and sort of aim at that, then you are at the North Celestial Pole. But in south, there's nothing called polar star. So you have to find it with a different method. So these are lots of interesting things going on. So basically, this is called a Magellanic cloud simply because Magellan thought that it was a cloud, and then later sort of realized that it is not, and then called it the Magellanic Cloud. I suppose somebody else called it the Magellanic Cloud, I suppose. Anyway, that's those pictures. So this is what they call a galactic core. So our galaxy is has got 3 spiral arms going in a spiral, obviously, with a little bulge in the middle, which has got a supermassive black hole. So this bit, so this is not the black hole, obviously. This is the dust lanes and gas and all that. There are a lot of star forming and all that going on in the middle. But the thing is, what I want to let you know is that we are not seeing anything beyond that, because it is so dense with this black hole. Nobody sees anything on the other side of this black hole. So basically we are only limited to about 180 degrees of stars and galaxies and all that. But then that is enough, I suppose. And the other interesting thing is that if you see this little dust lane, which is going up, and little 3 or 4 stars here, so that is called Rho Ophiuchus. I'm not really sure why that is. Rho is that Greek letter for R that you do in physics and all that. So it is called Ophiuchus. Don't know what that, but I was trying to get into it, but then I had no time to get into it. So that signifies the that dust lane which so connects to that area. That signifies the galactic core. So you can see how many stars. I mean, these are the stars that I caught, but then doesn't mean that's the only star. This Christian, that German chap who had gone into one of these little small areas and so enlarged it in his telescope about 10,000 times, had full of galaxies and stars. So basically, he said there's nothing. I mean, you cannot imagine how many stars and galaxies are around. He said it's an amazingly complex system, but it is beautiful to the nth degree, I can tell you. So that is again larger version of galactic core, and you can see that Rho Ophiuchus going up straight up with a little star cluster there. So this is when galactic core was rising. This is at about 2 o'clock in the morning. Even though you see this is again 20-second exposure. You see buildings and all that, and I could actually get into Photoshop and sort of bring them out very much better. But the thing is, then my galactic core goes completely washed out. So basically, didn't do that bit. But I want to show you is that again, I have this greenish yellow cast, which I never knew what was going on. I thought it's something wrong with my camera. And also you'll see that this little light there. Now, what do you think that is? That is not sunrise. That's a mine about 600 kilometers away. You can see how much light pollution is around. That light is from, that is 1,000 meters below, plus about 550 kilometers away. That light is from there. So you can imagine how much light pollution is around us. So this is another picture of galactic core, because I'm really fascinated about galactic core, but I'm not really sure whether you will be. I mean, sort of. So excuse me for sort of showing you galactic core after galactic core again. It is really obvious star forming region there. That's why it is white, and it is full of nuclear fusion going on. It is not fission, it is fusion, because what we do on Earth is nuclear fission, and what happens in the stars are nuclear fusion. So they make hydrogen and helium sort of get compressed together to make lots of other elements, including up to about iron, and if it is a large star cluster and all that, they go up to about gold. And if you are wearing gold, you can definitely say it comes from the stars. That's for sure, from nuclear fusion. I hope you like the picture, but then it is amazing to see this in real life. You cannot, I mean, you can sit down and watch this for hours. Simply, there's so much to see in these dark sites. Oh, I'm gone back. So again, so this is not galactic core. This is actually the front bit of the galactic core. There's no north, south, and east, west in the space. It's only wherever you see it. That's how it is. So at that site, this is the front of the galactic. This bit was in front of the galactic core, and these dark patches are basically dark nebulae. They are all dust and gas trying to form into that one of those like white patches where when they compress, they become star forming areas, and then they make stars and go white. Anyway, that is physics, and I have no idea how it all works out. But what I'm trying to show here is that this is that little microwave link. You can see how this is again 20-second exposure. You can see how much light it emits. The second thing is that that's a dome. You can see large Magellanic cloud and a small Magellanic cloud there. So there are two of them, which northern hemisphere people don't see till they come to southern hemisphere. This again at about 2 o'clock in the morning. You can see the road and everything else almost clearly. So it is amazing to see how much of light is being thrown out from the stars. So this again, a little site, a little picture that I want to show you. This is a water. This is a water tower that we have for that whole area. They say 1 shower a day, but then there are not very many people, so you can have 3 showers a day. Nothing will happen. We are not going to go out of water. So this is the dome. There's a 40-inch telescope in here, and they are imaging something because the trapdoor is open, looking towards that way, and the galaxy is basically so Milky Way is coming up with its large Magellanic cloud and small Magellanic cloud, and that. What do you think that is? That is sunrise? No, again, that is that's again so iron ore mine, which is about 1,000 kilometers away and 1,000 meters down. It's amazing how you see all these things. This is again 20-second exposure. Haven't done too many things to this. I only so cropped it from below. I just didn't want to have quite a bit of light coming up there. So I'm sure you see this little greenish hue there, yellowish greenish hue. So actually what I was thinking was initially it is some sort of problem with the camera sensor, but it is called it's a glow, in the atmospheric glow. It's in this all this electromagnetic sort of waves coming down, the atmosphere starts glowing. It glows green. It is nothing to do with northern lights and things like that. It is basically, they call it atmospheric glow. So not really sure how that all works out. I haven't gone down that line. So you can see a 14 millimeter lens. You can see this dome leaning towards the water tower. So I'm trying to see whether I can buy a tilt shift to see whether I can. I just want to actually hire a tilt shift lens before I get there next time, so that I can see whether I can get it straight. So anyway, so this is one of the other little pictures. So this is almost the same picture, but the thing is I wanted you to see this red glow in this water tower. What do you think that is? Nothing else has almost changed. It is large Magellanic cloud and small Magellanic cloud with the front part of the galaxy coming up. Give me a second. Coming up. So basically, this all red light was somebody's. That one of they have got this small LED red lights on the sort of forehead to see what's going on with their cameras and all that. So somebody, at the time that I was taking this 20-second exposure, somebody switched that on for about 2 seconds and then switched it off because he knew that I was taking a picture. But that 2 seconds, that is the light from that little LED red light. And as I said before, it takes about 20 to 30 minutes for eyes to get used to the dark. And if you see a bit of white light, then that completely negates the whole thing and you go back to zero, and then you have to wait another 30 minutes to get that night vision back. And I'll show you something. You see that little white light here? That is the front door of this dome. That is absolutely unusual to have any light in this site seen. So basically, they cover it with real dark, thick curtain so that nothing is spilled out. But somebody opened it, most probably. So anyway, so that is what it is. So while doing all these things, I tried a fast one, which I thought I'll get a mosaic of this whole Milky Way. So what I did was I went 20-second exposures, 14 millimeters, and ISO 6400. And I took, so I took about 15 frames in about 5 rows. And I overlapped each frame 50%, if you understand, from side to side and bottom up, so that I get all the stars and the program, which is called Microsoft Ice, if I'm not mistaken, that runs on PCs. So that seems to be one of the best programs to do those mosaics. So anyway, this is the result. So it made the dome straight, made the water tower straight. You can see the large Magellanic cloud and small Magellanic cloud. I think that little line is either a plane or one of those the Starlink satellites. So basically, that line is there, and you can see the Milky Way going across the sky. Only thing what I am regretting now is I should have waited. This is from about 1:30 to about 3:30 in the night that I took this. I should have waited a little bit, and then I should have waited till the core came to the middle rather than waited for, taking it that much. So basically, again, that door has still been open, and you can see that the light from that mine about 1,000 kilometers away. Here you can see this green glow, which they call the atmospheric glow. That is pretty good, pretty nicely seen here. So if you really see, there's another chap here trying to take a picture. He's actually one of my friends. So he's in the picture. But if you don't really look at him, with this, so Milky Way going across, I don't think anybody is worried over. Anybody's going to see him. So that is second. This is one, and then I did even a worse thing. So this is, I thought the second day I took pictures of, so I just took pictures 360 degrees across, and it is again 20 seconds, 6400, and I overlapped them about 25% because it was taking huge amount of time. So I went round and round, and then up to the zenith of the sky. And zenith is what they call it, at the 90 degrees of the sky, that is. And there are a huge number of photographs. I didn't think it will come right. It came right. I can't say it is right, but the thing is, it came like this. So if you really see, You can see the dome, and I don't know where the water tower has gone. I think that blob is most probably that. That's a little microwave link. That's a building, and that's a little road that we were talking about. So went around. There was a huge tree next to me. So that's the tree moving in the wind. I don't know what this white black blob is. So I don't know where that came from. Most don't know whether it is again in Microsoft Eyes. Not really sure where that came from, but also you can see this little grayish lines all over the place, and you can see the core of Milky Way here, and it spans all over across. But the thing is, I think number of pictures were not enough. That's what happened. And then the program did whatever it could do to fill up the gaps. That's what I feel. But next time I go, I'll take double the amount of pictures, which will take 2 nights, I'm sure, and see what comes up. Because if I have a crescent of Milky Way with the dome, that would be absolutely brilliant with starfield foreground. I mean, starfield all over the place rather than these patches. Anyway, so that is one of my little experiments which went not horribly wrong, but then reasonably wrong. There's nothing that I could do about it after I got it. So anyway, talking about image sensor, as I said, full frame image sensors are preferred. And you can actually astro modify all the DSLR. So what they do, so every DSLR sensor has got a IR cut filter and ultraviolet filters in the front of it. So basically what happens is all the infrared and ultraviolet get cut off, and then only visible light goes through. But if you remember the wavelengths, hydrogen alpha, which is the most commonest element in the universe, has got a wavelength which is closer to infrared. So basically what happens is these sort of filters cut off huge amount of light from this hydrogen alpha wavelength. So ultimately you get very bland looking washed out red images. So when you do this modification, they take those things off, and then basically CMOS sensor is basically there to take in all the light that it could. So basically what you have to remember is that you are trying to collect photons from sort of thousands to hundreds of thousands of light years, from hundreds of thousands of light years away. So every captured photon is gladly taken, and want to take every photon that comes down. So basically that is what this modification does. So it is called partial modification and full modification. If they take only IR filter out, then it is called partial, and if they take both the filters out, they call full. And so full is a modified sensor. So, but what you have to remember, all sensors. So now we are talking about CMOS sensors. All sensors are so monochrome. They don't see color. It is only monochrome. So there's a thing called Bayer matrix on it. It doesn't matter whether it is. I'm talking about CCD and CMOS. It doesn't really matter whether it is CCD or CMOS, because most of the digital cameras are CMOS sensors rather than CCD. CCDs are much more expensive for some reason. So this is what they call a Bayer matrix. So if this gray thing is the sensor, it only sensors in the monochrome. It only knows black or white. It is a digital thing. Either it is 0 or it is 1. If there's a photon falling into it, it becomes 1, making it really simple. It is not that simple. If it is, if it doesn't, then obviously there's nothing. So it is 0 or 1. So, but what they have done is they have put red, blue, and green filters on top of each pixel. So which is called the Bayer matrix. So what happens is, like from this side, on the right side of the picture, if it is a right filter, only right red light will pass through the filter, only green will pass through the filter, and only blue will pass through it. And on the other hand, also what they have done is they have twice the amount of green filters than red and blue. So that is because what they say is on Earth, there's more green things than blue and red things. So they cater for that. So basically, that makes matters very difficult when you imaging the heavens. Basically, there are very minimal things that are green in the cosmos. It's all either blue or red, or it can have somewhere in the middle some greenish tint, but then nothing very much green about it. So you can't take the Bayer matrix out because it is stuck to the sensor. So you're limited on that behalf. On that sense, you just can't do anything very much else because there's no green. If there's no green sort of photons coming up, then there's nothing very much that you can do because there's not much green things come down. So only you see red and blue most of the time in DSLRs. Not that it makes a huge issue. So best pixel size is a complex issue. There's a huge amount of maths there. So which I'm not really sure of, and I'm not a math sort of a guy. So basically, I have practically left it to the people who knows about it to deal with. Both Canon and Nikon has come up with factory astro-modified cameras, and they are DSLRs and mirrorless bodies. So Canon has come up with 3 of them up to now. So it is 20DA, 60DA. They are all crop sensors, and the latest one is RA, which is a full-size sensor with a pixel size of 5.36 microns. If Canon produces that, and as an astro-modified camera, I'm sure 5.36 microns will be enough to image all these things up to a certain point. And Nikon only has come up with one that is about 2015 or 16, I think. It's called D810A. I think it is not. It's not in production anymore for some reason. So there are other little important things that, again, as I said, focusing, and again, talking about Roshan's long exposure talk 2 days ago, focusing is really hard. Basically, there are aids to focus in this sort of situation. So you are talking about night sky, and it is nothing to do with any light anywhere except from stars. So basically, what you need to do is to get the brightest possible star and focus on that. So, and my sort of 5D Mark III can go up to about 10 times. So you have to find the star in the live view, make it 10 times, and then focus it up till it becomes the smallest blob on the live view screen, and then take the picture and see what comes up. So I have been reasonably lucky in that sort of sense. I could most of the stars that I have taken are pretty pinpoint. They're not big. They are not so that my focusing was not too bad. And basically, there is focusing aids. So in Canon RA, there is it can go up to 30 times sort of magnification in live view. One of the best things, so that you have a large star to focus on. Also, there is that little 3 green arrows. I'm not really sure what they call it, which can focus, which can point when those arrows come together. I haven't never used this because I haven't used my RA to image the stars yet. So I can't really say how it all works. But anyway, I just hope that they are good. And also this remote triggering of the shutter is very, very important, because you can't touch the camera because it is going on for 20 seconds. 20 seconds is a long time. It doesn't seem to be a long time, but when you're taking a picture, it's a hugely a long time. So that has to be sorted out. So Canon RA has got there's an app called Camera Connect app. It is via Bluetooth, so you can control everything from a distance with your phone. So you don't need to be in the cold. You can get into the room with the heater and then sort of control the camera and see the pictures too. So that's a brilliant idea. That's a good thing from Canon. So this is what I said was a focusing aid. It's called Batinov mask. It's exactly looks like what the picture shows. It's by a guy called Pavel Batinov. It's a Russian chap who made this. So this, when you try to focus, it comes up with 3 spikes from the star. So what you do is you make sure that 3 spikes meet at the star at one point. Then the star is in focus. So it's pretty easy. So it is pretty good thing to have. I have got a Batinov mask, but then I just couldn't find it to take a picture, so just got it from the internet. Anyway, so that is what it is. So applications to have, I think I have got this thing called PhotoPills, which is about 15 Australian dollars. Or if I'm not mistaken, I think it is 15 Australian rather than US. But anyway, I have never seen anything which is better than that. It shows you moonrise, moonset, sunrise, sunset, the nautical night, and sort of all sorts of names. There are too many things that I can even remember, but it the biggest thing that it gives is that you can make sure that you choose the right day if you want to do astro imaging as well as landscapes. So there are lots of people who combine landscape with astro imaging. So basically, they do a thing called light painting. So they take astro photograph while taking it for about 2 seconds. They go and put a flashlight onto something so that it comes up. So which is, I haven't gone down that line because I was not going to talk about landscape. So basically, that is a brilliant way of doing it. But PhotoPill shows you with augmented reality which day where the galactic core is going to come up. So, and there are, so this was done by a German chap by the name of Raphael Potts. So I just phoned him once to ask some complex thing. So with his really thick German accented English and my really thick Sinhalese accented English, we managed for about 45 after about 45 minutes we just managed to sort it out. So he's a brilliant guy. He never let go. I mean, I thought he would not want to talk to me that much, but he didn't let go. He spoke to me for about 45 minutes, and we got that thing sorted. So there's huge number of video clips in YouTube which teaches you what to do, and Raphael by himself comes up with a video a week sort of a thing. I think yesterday there was a video, or today there was a video from him. So if you join his video, you don't need to get PhotoPills, but the thing is, if you get PhotoPills, you will never regret it. So that's one of them. And there's another app called Star Chart, which is again have augmented reality. You can actually move the phone and find the star, because it's a brilliant way of finding your star, which is not that obvious. That's really nice. And the third app which I have just written about is that sort of the International Space Station spotter. So I tried to sort of photograph the International Space Station. It travels about, from my backyard, it travels about, say, about 1.5 seconds. It goes from one horizon to the other, and they're not really horizons, they're trees. So basically, there's not a single way of my getting a picture with a focus. So I got smudges, but never a picture. So basically, I'm going to take a little, because RA can do a little video thing. I want to do just take a video clip and see how it works, but haven't got to it yet. So that is one of the good things. And if it is just after sunset, you'll see this solar rays catching sun. It's the brightest thing in the sky, moving fast. It's amazing sight though. It's a brilliant thing. But only thing that there's no app for is rain. It rains and it will always rain. And if you have a camera out, it is bound to rain. So you need to have a thick plastic bag or garbage bag so that you can put into the camera rather than you. So basically, just have a garbage bag with thick plastic garbage bag, or two for that matter, because water and cameras don't go together, as Roshan said about 2 days ago. I'm absolutely sorry to hear that, Roshan. What happened to your camera? So narrowband. So this is the best way that I can explain this is that this is a view from a about 1,000 millimeter focus length telescope with a field of view of about 3.5 degrees. You can compare the moon, size of the moon. It is only 0.5 degrees. So you can fit multiple moons here. So basically, these are sort of CCD cameras which are made from as big ETA, ZO, and QHY. QHY and ZWO are these Chinese companies. And Orion was an American company bought by Chinese and tried to undercut everybody else, and they had to sell it back. I don't know, somebody else had bought it now. So anyway, it's big, and ETA are brilliant cameras, but when they are brilliant, they're really expensive. So you can't even go close. ZWO, the full frame ZWO will come to about 2,600. But the thing is, you have to remember they are cooled cameras too. So to come out 2,500 Australian. So they can be cooled up to -20. The real good ones can be to be cooled to about -40. So why are they being cooled? Because so there's a thing called dark current, which makes imaging really difficult in the long. So we are talking about narrowband. They image hours at a time. So it is not 20 seconds. They go for at least 15 minutes at a time. And then they go multiples of 15 minutes. They go for hours. So basically, when I say hours, they are literally hours. They talk about 5 hours, 6 hours of collecting photons from these deep sky objects, deep space objects, where they're really faint, but then they find it. So when this dark current causes lot of noise, so these are electronic noise which makes look like a star, but actually not a star. So they cool it to reduce that. So basically, most of these cameras are sort of monochrome, and so we are talking about four different filters. One is there's no filter, which is called luminance. Luminance is the amount of light which falls from that object to the sensor. Second thing is red, blue, and green. So those are visible colors. So, and then once you do that, then you can image on another three sort of wavelengths, like oxygen 3, sulfur 2, and basically go down the line of hydrogen alpha. So there are 7. You can get 7 images and get all those 7 together to get these amazing pictures of faraway galaxies and things like that. So these are always monochrome, very rarely in color, these cooled cameras. So this is the visible light range, and this is where everything falls. So we don't tend to do hydrogen beta for some reason, but we do hydrogen alpha, oxygen 3, and sulfur 2. Those are the wavelengths, and you can have very specific filters for that narrow spike. So that is why it is called narrowband in the first place. So that is my explanation, and basically nothing very much special there. Basically hydrogen alpha is, as I said, 656, and oxygen 3 is 501 nanometers. S2 is 672. So color depiction in astroimaging is another complete different science and art. It's a little bit of science and lots of art. So basically, there's a thing called Hubble palette. So Hubble telescope, when it went up, all the scientists got together, was dealing with it, and made a Hubble palette. And if you have seen Hubble pictures, what they do is they always say it is false color image. I'm sure you would have noticed that. So I first thought, why are they saying false color? Now I understand why. Because if you looked at that previous picture, hydrogen alpha falls into the red zone, and sort of sulfur 2 is almost at the infrared region. However, if you take a Hubble palette, hydrogen alpha goes as green. So that is a false color. So oxygen 2 is blue, which is pretty good, and sulfur 2 is red, which is pretty good too. So basically, each these bands are taken up. So they again, Hubble goes and sort of images for hours. They don't need to do night and day because they are in night always, except when there's no sun, and they have no sort of clouds to deal with. So they image for hours, and then what they do is they get this hydrogen alpha band and make it go green, and oxygen 2 go blue, and sulfur 2 goes red. So basically this is done through software. I don't know what software they use, but I will tell you what I use. So it is called Hubble palette. So there is a guy called Astro Drudis. He's a Spanish chap who lives in somewhere rural Spain, not in Madrid at all. So this guy images like nobody's business. He has 3 telescopes, which one next to Anglo-Australian dome, and one in Chile or someplace, and one in Spain. So he images every time and his pictures are brilliant. I haven't put one in. His pictures are brilliant. So he has got a Drudis palette. So he has his own palette to go by. So he's at that stage of he can make his own palette. So people will take it. So basically, so false color is not real visible. So basically, why there's this false color images are that will show way more details of the image than the normal visible light range. So that is why they do these 3 colors. So I just didn't know that. I had to ask this Rafael Pons about it, and then he's the guy who told me that too. So that's the reason, it seems. So I never knew that, why it is false color. So this is a thing called North American Nebula. North American Nebula, it is not American Nebula. It is called NGC 7000. So you can imagine there's not a single star here, right? So stars have been removed. There's only the nebulosity. So all this gas and dust, which is trying to combine to make stars. So basically, I'm not really 100% sure, but I'm 95% sure this is a Hubble palette. Because you cannot get such a picture without Hubble sort of a telescope. So there's no stars. They have taken the stars out. So if you really see normal depiction of North American Nebula, so that looks like North America, and so basically that is why it is called North America. You can see the amount of stars. Just Look at that, and that exactly the same thing. So I don't know whether this is Hubble palette too, but then I'm sure this is Hubble palette. So these were given to me by a guy called Max Whitby. If you know him, he's a PhD. His PhD is from, again, optics. Met him at the exactly the Anglo-Australian Dome. We took the astrophotographs together. Basically, what happened was that if you can remember, there's a program called Horizon in BBC. In 80s, if I'm not mistaken, he ran it. This Max Whitby ran it. So he's a brilliant guy. He's not too tall than me. He's my height, but the thing is, his brain is about 3 times mine. So he's a brilliant chap. Nice chap to know. Okay, let me show you my little foray into narrowband. So this is a hydrogen alpha imaging for 300 seconds, that is 5 minutes, of a nebula called Helix Nebula, which is also called by the name of God's Eye. Now, I'm not really sure whether you will agree with me, that doesn't look like an eye at all. And so this is only 300 seconds. So to complete this whole picture, I made another at least 3 hours of data. So I'm only showing you one slice of my little data, but I had about 1 hour of data, but this is only 300 seconds. And this is a nebula, which is a remnant from a supernova 700 light years away. Not that far though. I mean, thinking of Milky Way is 100,000 wide. So this is only 700 light years, okay? So that's not too bad. This is the real one. See the real one? This is called a God's Eye. I don't know what you call this. I would not even call that anything, if I'm not mistaken. So I'm just showing how much time it takes. So this is God's Eye. So it is called Helix Nebula because there was a supernova. Supernova is a star when star goes bang and it blows out when it finishes its full, which burns inside. So when it goes bang, this is what happens. This is if it is 700 light years away, we are looking at really 700 light years back to see this. So anyway, look at that and that. That's why it's a huge time-consuming hobby. So this is mine. So this is about 2 hours work, imaging in all 3 narrow bands. But anyway, there's huge amount of work to do. This is called Bat Nebula. It is also called Cosmic Bat Nebula. It is 2,100 light years away. This is again supernova remnant. So this is again a star which has exploded. This is remnant of it. So anyway, this is one part of it. There is if you think of a circle, this is about 30% of that circle. So there is another 70% of that circle to go. So I'm not really sure how far that I'm going to go to take all of that in. So I thought I'll put these things in, but it is not the best. If you can look at this star that has got a halo, so that is not enough data to deal with it. It should be one pinpoint, not pinpoint, it should be one blob, not a halo. That's one of those things. Okay, so let me tell you. So you get to this. This is one of the pictures that I got after trying to get Vela remnant. So there's a thing called Vela remnant, which I will show you, which is again a part of what is left from a supernova. So I wanted to image this. So I told the telescope at I telescope what to do and all those things, and then slept. Next morning, I get 3 gigabytes of this. What do you think? There we are. Can you see anything? Obviously not, because so there's a problem in tracking and finding this Vela Nebula. So it is a complete waste of night, a good cloudless night. So this, after about 3 weeks, I get this. After about another cloudless sky, and after about 3 hours of imaging next morning. So this is the part of Vela Nebula. This is hydrogen alpha. Only one. I didn't put anything else. It is not in the center of the picture. So basically, it has failed tracking. So these telescopes need to track the object, because Earth is moving. You need to keep the object in focus. So the tracking has failed. The first thing, it has completely failed even getting it. Second, the tracking has failed. There you go. That is the Vela Nebula. So it is in hydrogen alpha. It is going like, it's like a little bit of an arrow, a one-sided arrowhead. So there's huge amount on either side of it, but obviously I haven't gone down that line. Have got about 1.5 hours, about 1 hour of data. So one of these days I will finish the rest of it and get it organized into a color picture. So that is one of my things. So as I said, many things go wrong. If there's clouds, humidity, or wind, the roof closes. So observatory closes, that's about it. You're done for the night. So there's nothing that you can do about it. And then the computer can't find the thing. Then you get that gray screen. So that gone wrong. Then the tracking goes wrong. Then you see part of the thing or something else that you didn't want to image. And other biggest thing is data corruption, but now it is absolutely there. They have sorted it out so good that you almost never get data corruption these days. So this is one that I'm going to show you that went really well. But only thing is, my color image I couldn't find for last whole week. I went through my data drives, but I just couldn't find it. But I found the good black and white one. There you go. That's, you should have shown me the color one. Color one looked brilliant. This is the black and white. It is called Eta Carina Nebula. It is again star forming region. All these white areas are the star forming regions. They are all red in the color image. It's multiple stars and dust lanes and gas all over the place. And so this is 7,500 light years away, and across the nebula it is 230 light years, compared to our Milky Way, which is 100,000 light years across. This I show. This image I show so everybody who comes around, so that who will listen, saying that this is my success story. But there you go. That's one out of the lot. So telescopes. First thing, I don't own a telescope, because basically I cannot keep them. Just first thing, they're massive, they're big, and they're expensive. Second thing, and you have to maintain these things pretty carefully. You can't bump them. They can't fall. All those things. And living in a bottle class 8 in a city sort of situation, there's no point having one. However, that is not absolutely true. If I do narrowband imaging, then I only image from those 3 narrow bands. So light pollution doesn't matter. So I have ignored that bit. So basically, it could be a refractor or reflector. Reflector has basically 2 or 3. So primary mirror and secondary and tertiary mirrors to focus the object. That will reduce the size and the weight of the telescope. But refractors are like telescopes. Obviously telescopes. They're like lenses where you get all lenses and really, really heavy. So both of them needs maintenance, especially reflectors need a thing called collimation. Collimation is primary mirror has to be parallel with the secondary mirror. If they are off axis, then you cannot image because it be a blurry image. It is like what happened to Hubble in the first instance. But anyway, Hubble had something else going wrong. It is nothing to do with collimation, I don't think. And then you should go and polar align these things, which takes time. And I thought it is not worth it. Rather than I will go to Bangkok telescopes in the Anglo-Australian telescope site and then image from them. So basically, I don't own a telescope. And mounts. So you have to mount the telescope on a mount. So what they say is, even if you have a cheap telescope, you have to have the best mount, because if the mount is wrong, you will never get a reasonable image. So basically, it goes from about Australian dollars 728,000. I'm not talking about on high end. I'm just talking about medium sort of a mount. So, and then they are very high maintenance. You can't have dust in them and all sorts of things. You have to polar align them and balance them, and then you have to have a guiding going on. Then you have to have a guide scope, and then you have to have a computer attached to it to deal with the guide scope and the mount. There are millions of things that can go wrong. So, I mean, all these things can be automated. That has happened, like with iTelescope in Anglo-Australian telescope. But the thing is, with my work, it is not a possibility. That's completely nonsensical trying to do all these things. So the next best thing is basically iTelescope that I use. So they have got 3 banks of telescopes, one in Chile, one in North America, one in Australia, and one in Spain. That's 4. So basically, they are fully automated, fully computer controlled. So what you do is you write what you get the telescope that you want. You tell the telescope what to image, when to image, how long to image, and all that, and then basically set everything up and go to sleep. And then that images, and next morning all the images are downloaded into your computer. So you have got your images. These people are really user-friendly people. You can talk to them. So can you remember that picture that I showed, that grayed out field? So I have imaged 3 hours. So this is about $350 3 hours, but they never charge me. They just let it go, because those images I cannot use for anything. So that's a completely waste of time. And so basically they didn't charge me at all. So they are really reasonable people to deal with. So applications that I use. So it is called Astropixel processor. That's what I use. It is written by a Dutch guy by the name of Mabula Haverkamp. Brilliant guy. He's improving it every month, sort of a thing. It's brilliant, and it does most of the things it need to do, up to going in. So all the science bit is done there. I'm not going into that, because I myself is a novice in that. So basically, I'm trying to teach it is completely nonsensical. So that's why I'm not going into it. I tend to ask everybody when I have to do one of those. So basically, till all the science bit will happen in Astropixel processor, and all the arty thing will happen in Photoshop. So basically, end result of APP process is going to be a TIFF file, and basically that TIFF file is going to be taken into Photoshop and stretched and done all sorts of things. So that's how I do it. And there's a thing called Pixel Insight, which is the most popular in the world. Astropixel processor is around 150 Australian, and Pixel Insight is around 350 or 400 Australian. So basically, I haven't gone with that because I don't do that amount of things. So gone in with Astropixel processor. The guy who writes it knows me, so it's better. And then the Photoshop that we think that we know, but it has got so much that it can learn. So planetary applications, most important, then you can basically find what you want to do. There's a thing called Stellarium, that's the website. You can download it to your computer absolutely free. And this can even control a basic telescope mount. So it's that good. And the other one is called Cartesian, which is called map of the stars or something in French. Laya would know that, but I have got it, but I use Stellarium usually. Basically, I need to acknowledge Sam for technical support. Took lots of his time about 3 days ago, and proofreading showed me lots of spelling mistakes and encouraging to do this talk, which is I should be really thankful for that. And also Laya, who initially encouraged me to join PSSL. Otherwise, I wouldn't be here. And supporting me with advice for a long period of time. With that, I want to leave you with this. I hope you're all there, not to sleep. So basically, this is a Galactic Core, a time lapse of Galactic Core. Music is Swan Lake by Tchaikovsky and by London Philharmonic. Unfortunately, I had to edit the length because it was getting too long and too large, and the program was crashing. Anyway, let me do this.
The music is not coming through because I think you have to share with music sound.
Okay, sorry. There you go. That's about it.